This is lesson 15 of the Quantum Mechanics, a mini lecture series. So in the previous video, I talked about Rutherford's model of 1911, Rutherford's atomic model, which proposed a very dense positively charged nucleus and electrons somehow arranged around it. Okay, and there were several questions raised, like how are the electrons arranged around the nucleus? What prevents them from falling into the nucleus due to electrostatic attraction, and so on and so forth. Around 1913, a Danish physicist named Niels Bohr came along. He arrived at Manchester University, where Rutherford was, and he met the man, Rutherford, to work with his team. And Bohr wanted to explain atomic stability. That was his goal. He basically used Planck's relation, so Planck's quantization of electromagnetic radiation, EMR, and he used Rutherford's model as a starting point. Okay, and he came up with a more enhanced, a more refined model. Okay, also known as a semi-classical model. Okay, because it borrowed some ideas from classical physics, semi-classical. And Bohr thought that perhaps there are stable orbits, okay, which use the Planck-Einstein. This is called the Planck-Einstein relation. Planck-Einstein relation. So Bohr actually believed that perhaps this mathematical relation could explain the stability of atoms. And he came up with four postulates, four principles for his atomic model. First one is that electrons move in circular orbits, okay, due to electrostatic attraction. Electrostatic attraction. Circular orbits. Okay, take a hydrogen atom, the simplest atom. You've got one proton, one electron. There's an attraction there. So that's postulate number one. Postulate number two, electrons can only exist in specific locations around the nucleus in shells, okay, also called orbits or energy levels. And that explains stability. That explains why they're stable, why the electrons are stable. Okay, and only 2 electrons are allowed in the first shell, 8 in the second shell, and so on and so forth. His third postulate, to move between energy levels, electrons either absorb or emit electromagnetic radiation. They can only move, okay? I've used the word move, okay, just to give you an analogy. Think of like a person moving between, I don't know, 2 different platforms on a train station. So here's Bohr's picture. Here's a hydrogen, here's a proton, a nucleus, here's an electron. Suppose you got light coming in with energy HF. Okay, an electron gets excited, moves up one level, and then it jumps back down, releasing light in the process. And I'll give the symbol, and typically the symbol gamma, Greek symbol gamma, is given to denote a particle of light. Okay, a quantum, as Planck suggested, a quantum of electromagnetic radiation. Okay, a small chunk of light. Okay, so think of an analogy. A good analogy is think of a person. A person is low in energy. You give them an energy drink, they get excited. Okay, they jump up like an energy state, and eventually they'll crash. They'll come back down. Okay, back to the original state, just like an electron. And so the change, this symbol means change in, Greek symbol delta, change in energy between the two levels, simply given by the energy of the final state minus the energy of the initial state the electron is in. That's equal to HF. H is Planck's constant, a number, and F is the frequency of light. Okay, the change in energy of an electron is given by the final energy state minus the initial energy state. Okay, a very simple relationship.